Building conversion to an energy-efficient building. Improvement thermal transmittance of a higher educational building in Egypt. Abstract. Energy saving is one of the world's most important issues because of the lack of energy expected in the future, as the urgent need for efficient energy applications for buildings in Egypt is necessary to help reduce demand for cooling and efficient heating. Moreover, solar energy applications are not cheap even with their availability. That is why solar energy is not contributing to energy production, which is often the most expensive, despite rising natural gas and oil prices. On the other hand, many buildings in Egypt are characterized by poor design with respect to the ventilation and insulation system. The materials used for the construction of buildings are usually made of bricks, concrete, stone, and metal. There is no internal or external insulation. Later, these buildings have a bad internal climate characterization. Therefore, this paper aims at achieving the requirements of energy-efficient buildings in hot and dry climates, as well as to achieve new solutions for the reconstruction of those buildings. Then, we can significantly reduce power consumption to compare to current consumption. To achieve the main objective of this paper, all factors affecting the design of the building will be introduced to reach thermal comfort, such as building, steering, and envelope construction, as well as discussing the problems that have emerged in non-structural components such as external and internal walls, ceilings, openings, and other building components. On the other hand, this objective can be reached by verifying the experience of using various relevant technical solutions in developing countries in the same climatic conditions as traditional design elements in Egypt. The goal is to export the concept of energy-efficient buildings as much as possible to maximize indoor comfort by minimizing the adverse climate impact with minimal energy consumption. Keywords: energy consumption, energy efficient, building envelope, natural ventilation, thermal comfort. Introduction. The construction sector alone accounts above 33% of world energy consumption, which making it the biggest single supporter of the total energy intake. 1. The countries of the southeastern Mediterranean are expected to witness a population growth of 40 million and new housing units, reaching 24 million by 2032. Increasing population, housing, and improving living standards will therefore increase energy demand. As more families use electrical appliances such as washing machines, refrigerators, and air conditioners, the main reason for the rapid increase in electricity demand is the latest. As a result, primary energy consumption increased by about 50% between 2000 and 2009, and the final consumption of electricity almost doubled. Thus, the business-as-usual approach will double the final demand for electricity by 2020. The International Energy Agency asserts that energy efficiency improvements in buildings, appliances, transport, industry, and power generation represent the largest savings and the least expensive in emissions. 3. So, reducing electricity consumption will now most effective have environmental and economic advantages, however may also aid electricity safety and a cleaner environment. At the national level, this will also provide financial resources for the needy sectors such as health and education. At the individual level, the family budget will be relaxed. The correct approach starts from the architectural design stage and the preparation of the initial drawings. In addition, simple strategies such as orientation, insulation, window size, and shading will reduce net energy demand by about 30% as well as improve indoor comfort. Before, the building design of depended on construction rehearses created after the experiment and the realization of right or wrong proportions, but now, designer changes the building's designs significantly and turn out to be extra strength efficient. There were 3 important adjustments inside the way we construct buildings. Thermal insulation changing. Enhance air tightness. Air conditions emergence and heating systems. 4. 2 basic principles in energy-efficient building design. A. Building orientation. Primarily, the building orientation has a great effect on energy consumption. Quantity, ratio, orientation of the glazed surface are 3 criteria for this case, where the large glass surface on the southern oasis of the constructing increases the heat absorption capability of the building inside the wintry weather. To reduce sun warmth acquisition throughout summer season, the glazed surface ought to be furnished with appropriate shading devices. 5. B. Building form. Building shape is a very essential detail at an early degree of design and strongly affects the building energy consumption. The building with compact form is higher than others. Furthermore, L-shaped building expends extra energy than a cubic meter because of the span of the wall surface, resulting in more heat losses. 6. C. Shading. Shading limits solar radiation, where it is most important in hot weather, especially in summer. 4. To control solar heat gain rates, low-cost solar crushers can be absorbed as they take in and reflect a big part of sunlight before reaching windows. On the other hand, the use of shading devices will be appropriate in the summer because it will reduce the cooling energy, such as the hanging devices, umbrellas, and curtains that can be used for this purpose. 5. 3. Building envelope. Building envelope controls the heat exchange among external and internal areas. The two principal thoughts to decrease this thermal exchange are insulation and the thermal mass. Thermal mass is powerful while the temperature distinction among day and night is more 140 degrees Celsius. 7. Materials with a huge thermal mass have a high ability to heat storage as these materials are heavyweight and have a high density such as clay bricks and natural stone, and therefore they can assimilate and store heat amid the day and afterward discharged around evening time. Insulation materials decrease heat transfer during building casing because of low thermal conductivity, under 0.1 W/m. Little air bubbles also decrease heat transfer. This is why insulation materials have lightweight and low density. During warmer regions, well-insulated buildings are characterized by lower cooling loads due to lower heat transfer from the outdoor to the inner. This, in turn, results in better internal quality, which reduces the comfort and productivity of individuals, as the need for additional cooling loads is reduced. Insulation materials vary between fibers or cell insulation, and should keep going as long as the building is in place, approximately 50 years. A thermal insulation position. Insulation can be carried out to various locations within the building, either indoor, outdoor, or among two layers as follows. Indoor insulation makes solar heat penetrate through the external wall. So, the thermal transfer rate is reduced in the insulation layer. This choice is effective in cold atmospheres with warming as a main power requirement. If there should be an occurrence of heat exchange from internal to external, internal warmth won't be consumed from the wall. Outdoor insulation decreases the heat flow at the external building's envelope. Therefore, this solution is preferred in hot climates. 8. Insulation between thermal mass layers is a combination of above alternatives, the most appropriate for blended atmospheres that require cooling and heating. It is a great solution, because the protection material is surrounded by two strong components, which provides sturdiness. However, it's far hard to replace them. The simplest way to choose the appropriate protection material is to compare U values. It means that the heat exchange limit of the materials. Lower U value, better protection limit. B. Wall construction. The wall's materials choice need to make sure the desired of the building energy performance. Because the walls often occupy the building's biggest surface, their U value, thermal transmittance, significantly affects cooling request. For calculation of the U value see page 4. This consists of dark, closed, walls and windows and doors, glass and body. It is worth noting that the more materials used in building and finishing the walls more resistant to external environmental factors, the lower the thermal conductivity and also the rate of transfer of thermal energy inside the building. Alongside the wall thermal conductivity, also the color and the surface texture affect the indoor cooling load. Mild colored wall displays extra energy than a dark one. Rough surface makes shade on itself. So, it decreases the heat retention. In the two cases, thermal transmission decreased beside the cooling load. See roof construction. The roof of the building receives most of the sun's rays per square meter. In this way, it's important the rooftop has a high thermal capacity and thermal insulation. Like the wall, the U value are the thermal transmittance indicator for the roof. Figure 1 indicates two different rooftop constructions. One is insulated and the alternative isn't. By evaluating the thermal transmittance of those rooftops, we see that the insulated roof has a very lower thermal transmittance and accordingly a higher thermal resistance. So, rooftop insulation is most favored for all atmospheres. The roof shading components, for example, solar thermal, pergolas, and so forth decrease the solar radiation and the heat load on the rooftop. 8. Above all, a basic method to decrease the cooling load by coloring the rooftop with light color such as white painting which reflects much sun heat, and along these lines it requires longer time for warm up the rooftop. So, it takes longer before warm the indoor space, this operation called the time lag. D. Thermal bridges. Thermal bridges problem is that it interrupts the insulation layer. This makes thermal switch on the building components connections, which includes wall floor, and wall window connections, as in figure 2, left. In case of building without correct insulated, thermal bridges constitute low losses, always under 20%, as compared with the energy losses through the building envelope, but thermal bridges might also cause condensation issues amid winter in humid areas, see figure 4, right. When the roof and walls are all around insulated, the losses percent because of thermal bridges turns into high, over 30%, in comparison with losses via the envelope. So, in energy-efficient buildings, Thermal bridges need to be avoided. 9. Above all, the reinforced concrete structure are the common construction method in the Mediterranean region, which contain columns, beams, and floor slabs, and brick walls. This all enhances the presence of thermal bridges. Solve thermal bridges as following. For interior insulation, the solution complex, because the wall and roof should be wrapped with insulation for around 50 cm from the wall. Continuous external insulation is an ideal strategy to resolve thermal bridges at floor-wall connection. When insulation between two construction layers, the problem can be solved by adding to the framework edge 3 cm polystyrene, earlier than adducing concrete. Glazing. In the same area, windows may lose heat around 5 times more than a wall. So, the window glazing U value must be improving or taken into consideration. Glazing types. Single glazing, the normal type in the Middle East, as it's the least expensive, it additionally has the biggest thermal transmittance. So, it produces a huge heat exchange. Double glazing, often utilized for sound decrease. In addition, it reduces the amount of heat transfer and cooling load. Glazing specifications. Glazing thermal transmittance, which is comparable for roofs and walls, such as single glazing, U value equals 5.88 W/m2c. Double glazing, U value equals 2.88 W/m2c. By adding argon to the air cavity, the U value can be lower. To calculate the whole window thermal transmittance, the window frame must be taken into consideration. G value, indicate the energy transmission through the glass, as in figure 3. To decrease face light, G value ought to be higher. However, to reduce glare in spaces with an exceptionally external light, a decreased G value ought to be conceded. The emissivity, measure of thermal radiation which emitted by the glass. To improve glass overall performance, we will use special low-emission coatings, which we referred to as low-E glass. Emissivity of the same glass has around 0.840. Emissivity of pyrolytic covering can accomplish roughly 0.40010. F. Air tightness in buildings. Heat loss and heat gain also caused by tiny air gaps between layer of building elements or components such as walls, doors, and windows. So, air tightness must be addressed during the selection of bonding materials between building elements. This must ensure that the seal can be done correctly. On the other hand, the implementing agency have to know the significance of air tightness and subsequently implement during the various stages of building construction. Above all, the air gap width has to calculated precisely on sketches. So, the site supervisor can know the locations of the critical points. The following points have to take into consideration during the construction phase. Wall. Make certain to fill the mortar junction completely. Avoid gaps among the elements that appeared through the construction of walls and roof. Windows and exterior doors. Make certain that the windows and doors are included with the air strips to get a suitable tight arbitrator when closing. All pieces in the building have to closed using permanent materials like plaster and rubber. G. Material preference. The building materials preference is a substantial part of passive architecture design. Beside the architectural features, thermal properties have to take into consideration when decide to select building materials. Ameliorating the building energy performance need to be assessed the following characteristics. Thermal transmittance, heat transfer coefficient, U value, W/m2c. This is the sum of the resistors, RC, for each building material and the external surface resistors, RSO, and the envelope interfaces as in figure 4. The R value, M2C/W. This is the material thermal resistance, and calculated from relation, R equals T/M2C/W, T, material thickness in meter, dot, the thermal conductivity of material. H. Envelope requirements. The energy-efficient buildings envelope recommendations are lists in the following table in summer and winter climate. It depends on the number of building floors. Table 2. The meaning of light construction, traditional buildings constructed with wood walls, floors, and roof, and heavy construction, traditional buildings constructed with massive walls, concrete blocks, and concrete unit. 4 common thermal building problems in hot regions. The aim of house building is to get the population free from external conditions like sun rays and humidity in summer and snow, rains, and windstorm in winter. Thus, a desirable indoor environment for buildings should be established. The cause of worldwide concern over the energy resources and weather is to identify more factors for design buildings. Architects and/or designers must study the climate features of their environmental designs. Moreover, according to this awareness, they can classify building thermal problems and propose ways to get rid of them, which is known as a climate design, concerning the characteristics of climate in the desired region. To introduce a building with a good indoor climate and thermal comfort in all climates, the common building thermal problems must first be determining. The below points are commonly referred to in several studies. Higher temperature, higher solar radiation, high RH level or moisture, increase excessive heat in the summer, heat loss during the winter. 11. Thermal radiation from sun. One of the factors must be taken into consideration in studying Egyptian climate as well. High temperature, summer heat gains and lose to achieve thermal comfort and good indoor climate. The objective in this study is decrease the consumption in building energy, achieve a higher thermal comfort level. In this paper, a typical building, modern academy for engineering and technology, will be analyzed, which construction in El Mokattam, Cairo City, Egypt. For this purpose, the properties of various parts of the building will be studied and analyzed. Analyze an educational institution building, architectural department. The architectural department building considers a relative large educational building. The project built in 1993. It includes 5 floors and floor area of 2,414 square meters. All floors of the building used for engineering educational purposes. The project direction is south-north, and not attached buildings around it. Figure 4, up, layout of the modern academy, bottom, modern academy architectural building, basement, ground, typical, and roof, floors. The building has small natural ventilation windows because it relies heavily on central air conditioning, which causes thermal discomfort in summer when power is off. 6. Building envelope characteristics. A. Outside walls characteristics. The outside wall is one of the most important part of the building. Lots of heat loss through non-insulated walls. The wall's exterior insulation is the best to increase the energy efficient. Reducing the cooling and heating requirements of buildings depends on the insulation ways, which known as the thermal transmittance. It refers to the flow of heat within 1 square meter of the wall at a constant temperature difference of 1 degree Celsius. Table 3 show the materials used to build and finish the building walls, from internal to external. Table 3. The project wall materials. Exterior wall not insulated. The thermal transmittance proposed by the building code isn't over to 0.8 W/m2 degree C. But the realized thermal transmittance is 1.84 W/m2 degree C and is far from the proposed U value requirements. See Figure 7. Figure 7, roof construction cross-section, no thermal insulation in it. The roof thermal transmittance is 1.70 W/m2 C. See slab properties. The building slab insulation characteristics show in the following table, from up to down. Table V. The slab cross-section of the building. By the building code, the U value assumed is 1.5 W/m2 C, see Table 2, while the achieved U value is 1.70 W/m2 C. For details, see Figure 8. Figure 8, slab construction cross-section. Floor coating with marble tiles which near of reinforced concrete layer. This usually produced problems like condensation and mold growth under the floor coating. D. Windows and exterior doors. The building windows are single glazed and aluminum frame. It has characteristics as follow. Total solar heat gain coefficient, SHGC, equals 0.76. Total solar transmittance, T, equals 0.81. The thermal transmittance, U value, equals 3.5 W/m superscript 2C. 7. Building conversion to an energy-efficient building. We will improve the previous educational institution project to an energy-efficient building. So, a lot of factors ought to be conceded as follow. A. Wall properties, wall insulation. Improving the external wall properties demand reducing the U value to reach less than 0.8 W/m2OC12. To reduce it, we must use the thermal insulation 13. The heat insulation layer thickness must be between 10 to 60 cm. 14. Table 6 show a recommended roof material, from indoor to outdoor. Table 6. The wall construction characteristics after conversion. To improve external walls thermal transmittance, a cavity insulation layer is applied which contributes to 82% of the whole component thermal resistance. As a result, the U value of 0.20 W/m superscript 2C is achieved, less than 0.8 W/m superscript 2C. Figure 9, the conversed wall construction cross-section. By adding a thermal insulation layer, polyethylene, and a layer of gypsum board, The U value of the wall is improved until its value reached to 0.20 W/m superscript 2c. B. Roof properties, roof insulation. The roof thermal transmittance must equals 0.412. To reach it, insulation layer should in average 20 to 40 cm 14. So, a foam glass layer insulation is provided over RC which it not allows the sun heat to reach the concrete slab and inside building. Furthermore, when waterproof layer becomes broken, foam glass no longer able moisture to spread throughout the roof. 15. Table 7 show a recommended roof material, from down to up. Table 7. The properties of roof construction after conversion. To improve the roof U value, a layer of foam glass is applied which was 1.70 W/m superscript 2c after changing. Thermal transmittance reached to 0.18 W/m superscript 2c, less than 0.4 W/m superscript 2c. Figure 10, the conversed roof construction cross-section. By adding a thermal insulation layer, foam glass, the wall construction is improved. Furthermore, the bitumen 2 layers act to a vapor barrier. The wall thermal transmittance is improved until it's reached to 0.18 W/m superscript 2c. C. Slab properties, slab insulation. The building slab consists of reinforced concrete. Its higher thermal transmittance is 1.68 W/m superscript 2c. We should reduce this value to less than 1.5 W/m superscript 2c. 12. Over the concrete slab, a layer of polystyrene should be, see figure 15. To reduce the building air infiltration, links between exterior wall and slab foundation must be closed. 4. A recommended slab construction material and their properties as in Table 6, from down to up. Table 8. The slab characteristics after conversion. For slab, the required thermal transmittance must not exceed 1.5 W/m superscript 2c. The building slab U value is 1.68 W/m superscript 2c. To improve this value, a layer of extruded polystyrene over concrete slab is applied. As a result, the U value of 0.824 W/m superscript 2c is achieved. For details, see Figure 11. Figure 11, cross-section of the conversed slab construction. As a vapor barrier, a bitumen layer acts which allows passing the moisture in a slow, due to extruded polystyrene compressive strength, controlled manner used. D. Windows and external doors. Building windows with high glazing characteristics could make any building comfortable. The buildings with perfect thermal transmittance. In summer, the outdoor temperature moves the inner glass surface temperatures down near of the room air temperature. So, it causes inconvenience because of drafts and brilliant heat loss. Windows which have a minimum thermal transmittance is better choice for this trouble. In hot weather climates, all windows in buildings should have minimum solar heat gain coefficient values. In order to block the sun heat to enter the building. Low heat gain coatings will decrease outside heat gain beside achieving comfortable views and daylight. Good windows should have a thermal transmittance equals 1.3 W/m superscript 2c and SHGC equals 0.29 or less. To do that, coating building windows by low heat gain coatings. Or use double low E glazing windows in new building. On the other hand, exterior doors should have a U value up to 1.25 W/m superscript 2c. For exterior doors, steel doors, fiberglass doors, and stave core are recommended materials which give a good overall performance in phases moisture motion, chemical damages, and thermal movement. 11. E. Improving the building envelope transmission losses. The building thermal insulation is greatly improved compared with the original building. Specific transmission losses, U value, of the original building shows in the following table before and after conversion. 8. Conclusion. The study shows the next advantages of energy-efficient project characteristics by using the building energy outside as in Egypt, during the hot summer and cold winter in addition to the important differences between day and night. To improve the external walls U value, a cavity insulation layer should have applied to achieve a lower U value which contributes to 82% of the whole component thermal resistance. Improving the roof U value by applied a layer of foam glass which achieve a U value less than 0.4 W/m superscript 2c. To improve the building slab's U value, a layer of extruded polystyrene over concrete slab is applied which achieve a U value less than 1.5 W/m superscript 2c. Coating building windows by low heat gain coatings. Or use double low E glazing windows and low solar shading coefficient factor. Installing the exterior doors with U value up to 1.25 W/m superscript 2c. Design process and implementing energy efficient projects faces many challenges as follow. Components availability, Existence and best warranty. People accept and understand these new applications and motivate them. Lowering energy prices to drive people to use. Designing process energy-efficient projects isn't one-man show which done by the designer, customers, and developers also play a key role in this process and therefore all actors have the same responsibility. Architects with experience and expertise in this area can be the initiators of designing energy-efficient buildings. Hence their effective role in influencing developers and customers. Customers should also be informed about the amount of energy and costs that can be saved through effective energy building. Acknowledgement. First author grateful to the Department of Architecture at the College of Architecture and Planning in Qasim University for the encouragement and support. Second author grateful to the Department of Architecture at College of Fine Arts in Helwan University for the encouragement and support. Author and affiliation. Sherif El Said El Said, graduated from Faculty of Engineering, and Shams University, Egypt in 2004, then obtained a master's degree from Cairo University in 2007 and PhD degree in 2014. Now, he working as an assistant professor in Department of Architecture, College of Architecture and Planning, Qasim University, Kingdom of Saudi Arabia. Ahmed Yehia Ismail, graduated from Faculty of Fine Arts, Helwan University, Egypt in 1999, then obtained a master's degree from Helwan University in 2003 and PhD degree in 2009. He obtained the associate professorship promotion in 2016. Now, he working as an associate professor in Department of Architecture, College of Fine Arts, Helwan University, Cairo, Egypt.